Swayam Prabha. Digital India. Educated India.
So the previous one, we introduced the multi-skill concept that we can couple a continuum approach like FEM with DM to solve all kind of boundary value problem here. Here is just an extension. Now I wanted to show that we can use the same concept, coupling approach, coupling concept, to couple material point method with DM. And so you would wonder why. And the reason that we wish really to tackle a lot of important large deformation problems here. Okay, and so the problem can be represented in such a way. For example, the problem showed before, this would be the famous Kobe earthquake picture after the earthquake. Though the sand foundation is liquefied and cause the collapse of this building here. And this is the famous California debris flow situations where after big rainfall you generate such a large deformation failure. Another thing would be this the embankment dam collapse problem. All involve a large deformation that are, for saturated or unsaturated soil and different loading conditions here. Okay. And also in the earthquake situations, normally we need to assume a complicated bounding surface model to capture the cyclic behavior of the soil under dynamic load, and then the model itself is so complicated, and then you need really to select long time to understand in the first place before you can implement for that purpose here. So what we do is now we want to further extend this computational multi-skill modeling approach, and then to consider a coupling of DEM again for this RV and the green skill, and then with this MPM material point method, and then to solve a boundary value problem here. And so the coupling philosophy is still according to this hierarchical manner here for each material point that a quick introduction, what is the material point? Material point method is different than the mesh-based finite element method. It's basically using a Eulerian background mesh, and then in conjunction with the Lagrange describes the material point. This crosses material point, and this is background mesh, and then to solve a problem here, you get a certain problem. Again, the material point will carry on what are the material response and the material state, material parameters. These parameters will be interpolated with a nearby node point of this the background mesh here. And once you get all the parameters, and the governing equation will be solved according to this Eulerian nodes here. And when it's solved, and then you can really to further interpolate and then to map to this surrounding Lagrange material point here. And then the Eulerian background mesh can be further resetted to the original point, and where you can update the material point. And so this is the way what we call a particle-based method, and can overcome the typical difficulty or issues encountered by FEM. And for FEM, if you want to deal with the large deformation, you have to consider the mesh distortion and then the remeshing and other procedures. But this can be quite challenging if you want to deal with in a multi-skill approach, because each macrostructure represented by the RV information is attributed to a material point. When you do meshing, and then the whole thing, the material point can lose such physical features. But if you just put in the Lagrange material point, this Lagrange material point in MPM can be persistent, and when we do this resetting the mesh, and so this can handle large deformation pretty well here. For the DM, again, that we can incorporate this discrete element features and any using linear or nonlinear content model and use a idealized or realistic product shape for that purpose here. And so the idea is for a boundary value problem, we use a material point method to discrete the domain. And then at each Lagrange material point, and we embed a RVE, a discrete element RVE, and using the corresponding deformation condition, the boundary condition, we solve this RVE, and then we extract the required variables like stress and returned to this RVE material point, and then continue this RVE solution to get this one. And so this whole thing, and then offer quite a similar advantage that I showed before. Okay, and then this also can really to provide a capability to simulate a larger deformation problems. Okay, and where FEM and DM coupling may not. And so this one again that we can have other capability, but I want to show a couple of examples. First example would be the rigid footing one. Okay, and rigid footing one, we can really to look at the similar problem, but now we can really change this RV level to present a dense soil foundation, medium dense, or very loose soil foundation case, and under the same footing here. And then for a dense, and we can generate a very well-defined general shear failure patterns. And for a medium dense, we have this so-called local shear failure. Well, for loose soil foundations, you can generate a punching. So the shear failure will be confined very near in the neighborhood of this footing at the tape part. Okay, but for the dense and general shear failure mode, you have a well-defined shear mode, which is generate a very larger area of this height at the ground level here. So this represents a different failure mode, and which is typically larger deformation here. This is further recap of this failure mode here. And you can see here that this is shear deformation for the 3 failure mode. And this is a displacement distributions. And then this is the further we homogenize the void ratio in each RVE during the process or at the final failure mode. And this void ratio correlates with the shear deformation pretty well. And also the cumulative particle rotation in each RVE can also be well defined as an indicator of this shear deformation as shown on the right. So theta is a particle rotation each RVE here, and then this is the void ratio. So this all correlate with the classical soil mechanics or geotech foundation engineering theory pretty well. Another large deformation problem I want to show is this seabed anchor pull-out. And imagine that you have a seabed structure, you have an offshore structure like oil platform or other kind of like structure you want to anchor it at the seabed soil here. These are the typical seabed anchors we design here. Okay, there a special kind of thing is a plate form, like this is the second one. Okay, and then used really to anchor, use a cable and connect to this offshore platform to anchor it. Yeah. Okay. This of course this structure can be a floater structure here. Okay. And then so this platform under a different loading case, wind and wave load can really to pull the cables and further can pull this anchor out. And so this is the bearing capacity of this anchor, and the different pulling forces is a design problem for this anchor for this seabed anchor here. Okay, and first we can simulate a so-called a horizontal anchor. If the anchor is placed horizontally in the seabed here, and then pulled out and vertically out here, and so this is a pull out of a horizontal anchor that we simulate a half domain. So only the right hand half of this anchor is simulated. And so when we pull out and in a dense sample, and it really can generate a shear band penetrate through the surface. But if the loose one, and it will be rather confined here. And another case, if we put this anchor earth just like this second it's vertical, and then we pull it horizontally to the right? And then it's quite interesting that the failure pattern can be different than previous one. And then so when we pull this anchor to the right, and then the sand in front of it will be pushed, and then form a shear band penetrated through the seabed surface. But behind this anchor plate, and then this will generate a loosened part, and then this loosened part will generate another collapse mechanism, and so another shear band penetrated through the surface behind it, and then also felt by the seabed surface here. This is further illustration. This is displacement. This is a equivalent shear strain, and so in front of it you have a single shear band penetrated, but beforehand and then before it and behind it, and then you have a two shear band. One is initially at the plate tape at the top part, and the other is from this the bottom part here. Okay, so this is a collapse mechanism, and this is a shear failure mechanism here, right? So these are the simulation again that we use DEM and MPM for the carpeting simulation here. This is the further illustration that for a vertically placed anchor, and when we pull out on the right to the right and form a shear band from the failure here. And also this whole thing pull out will depend on the bearing depth. This is the shallow bearing depth, which here H is the head when we buried the depth. The depth we buried the plate, the center part, and then B represent the width here. When we buried it deeper, and then like H over B change from 2 to 5, and then you can see that in the dense part, it still can ready to generate a shear band that are filled by the seabed surface, but loose samples, the surface will hardly fill it. Okay, this can be better indicated by this rotation, and then particle rotation indicated shear band. And quite interesting, if we further bury this anchor deeper until this H over B reach to 8, and you can see in the dense part, and then you can feel a locally circulation mechanism. So what does this mean? That before the anchors, the sand will be pushed, but it won't really push to the top, because the bearing depth and also the confinement is high, and then the sand will be pushed to the top and circulated over the top of this plate, and then to fill the hole generated behind this anchor. This form a almost nearly a circular mechanisms, and with the top of the anchor as a center, rough center. And so this is very interesting local shear failure patterns in a very deep bearing. Okay, this happened for the dense sand case. For loose sand case, and then the failure is not apparent, but it remains local here. And then again, that for saturated soil case, we can use either a LBM coupled with DEM, or we use a fully resolved CFD DEM for the coupling here. And later on, I will show that kind of a CFD DEM coupling for maybe tomorrow's lecture. But that one, the fully resolved DNS DEM coupling option can be quite computational expensive. So what we do is for the saturated soil case, again that we use this UP formulation we mentioned before, and we use this Tasakism. Here we use we assume that the solid grain and fluid is incompressible, and we consider fully resolved one. And for the DM or each material point, we consider M band with a mixture of the DM with a fluid phase here. And for the solid phase, and then we use the DM to simulate it and use Tasaki's principal effective stress to extract the effective stress one, as I mentioned. To solve this mass conservation equation, we can consider UVP formulation. For UP formulation, typically we only consider quasi-static one. But for this UVP, V means velocity, and then we can consider a dynamic problem. This is also an advantage pertaining associated with MPM. We can easily handle a dynamic problem as well here. And then this is further momentum equations that we need to solve here. We can consider the drag force between the solid phase and the fluid phase in the simulations to consider dynamic cases here, right? Again, here is basically repeat that we apply this Tasaki's effective stress principle for these particle scale simulations to consider that the DM will return us with a effective stress quantity that through resolving all these particles in interparticle force to form these stress terms here. Okay, and also we can extract other microstructure quantities like permeability from this DM simulation here. Numerical part, and we develop a fractional step method. And then first we solve intermediate, we solve this velocity and pressure, and then we update velocity pressure for the solid, and then to this fluid here. Okay, and then we generate a set of intermediate velocity for the particles and for the solid and for the fluid, and then we solve for the pore pressure. And after we solve the pore pressure, and we further update a set of this velocity for both solid and fracture. This is what we call a fractional step method. Okay. And we do some benchmarks. The first benchmark is the 1D consolidation again. For the 1D consolidation, then we have a saturated granular media and subject to a ground surface surcharge, and then we can use DM to do some kind of simple 2D bacterial shear, and then at a small deformation. From the deformation, we can do a correlation to extract the elastic parameter K and J, and this K and J will be used for this Tasakis analytical solution for this 1D compression, right? And then these are the parameters we used. These are the compression that for the 1D consolidation test. These are the top surface segment, and these are the excess pore pressure changes here. I would say these are the excess pore pressure changes, get a different time step, and these are the segment changes here. Another thing that we validate would be cyclic shaking here. We have a saturated soil domain, and then at all these boundaries again that we apply for a undrained condition is impermeable, and then it's subject to this sinusoidal horizontal shaking, like a shaking table, and we shake it horizontally. Also, the whole domain is subject to gravity load. Okay, and then we insert two different RVEs. One is dense RVE, one is medium dense. We compare their response here. So it's going to be hydromechanical coupling for this case. And here the excess pore pressure in the dense packing here. And during this shaking, and then the positive and negative pore pressure will alternate appearing at the two left and right part of this one, but there's no apparent buildup of excessive pore pressure in this dense packing here. And but for the medium dense, if you look at the response, here is the displacement here. When we shear it, and then the displacement, well, initially is relatively uniform, but due to the unsymmetric buildup of excess pore pressure in the medium packing case, essentially at a certain after certain cyclic loading, and then you can really find that the final deformation will become built up, and you form this permanent deformation. That this will give us a so-called cyclic liquefaction case here. And this is a comparison that for a dense case on the left, you have an alternating change of this excess pore pressure, but no build up. But for a medium packing case, medium dense case, that during the different cyclic load process, and then there will be a apparent buildup of excess pore pressure. This buildup of excess pore pressure will reduce the effective stress of the soil body, and then will cause collapse or permanent deformation of the soil. This is further comparison case that when we monitor the three locations, A at the ground surface, B in the middle, and C at the bottom. And then the confinement surcharge and can really affect the confinement affect the response. And then essentially for dense and for A, B, C, their response more or less is quite similar. There's no buildup of excess pore pressure. But for a medium dense case at the ground surface, the buildup of pore pressure is quite significant, as they show the blue ones. And the medium is medium confined, and the buildup is not so significant as the ground surface. And the lower part, at the bottom part, the confinement is high, and then the buildup is quite mild. And so what we observe from the simulation is that the confinement matters, and also the density matters. So density and confinement, the two combined together, give us a combination, unique indication of this state. So indeed, and for saturated sand, is a quite apparent state dependency if their apparent features and affect their mechanical response, like a liquefaction. This is the further analysis that if we look at the medium and dense, and for the sediment for displacement dense is almost vertical, almost there's no change. For the medium dense, it's really getting settled down quite significantly, and because of liquefaction. And also, if we compare the shear modulus, okay, in terms of this in this plot, and then the red one give us after certain cyclic, and the shear modulus remain quite similar, but the shear degradation in terms of this modulus is quite significant for the medium case. You initially have quite a similar one, but then later on will reduce to almost zero here. Also, if we look at the before and after the liquefaction occurs in the medium and dense case, the contact force network at point B is quite a significant different. For liquefaction, you have the strong contact force chain, which help to sustain this external shearing. But after liquefaction, and a very small and thin contact force, which means that at that point, the whole packing can hardly sustain the external shear. And so this is the observing. We just use this example to demonstrate the feature here. We can also look at the collapsed saturated soil column, and this is the simulation of a collapse at different time step. Okay, and for a saturated case compared with a dry case. Again, here we make assumption where we don't consider separation of the water with the material point, and then with the sand particle, with the soil particle in this case here, right? Then, but essentially, this will generate a certain detailed aspect that we can really analyze for the problem here, and especially that we don't really hold the water with the soil sample. Sometimes that can generate certain negative sepal pressure, which affect their, for example, their the collapse distance, the runout distance that we monitoring. Okay. Another interesting problem we tackled is a wave propagation problem in anisotropic saturated soil. Again, quite a similar problem as the first one we demonstrated. You have a saturated soil domain, which is with undrained condition applied to the surrounding here. At the ground surface, you have a surcharge. At the top part, we apply a punch load here. You have a sinusoidal punching load, and after that we remove it, and so there's no load anymore. We look at the dynamic response of wave propagation in such a soil domain and subject to this punch and pass the punch load here. Okay, and for the soils, and we generated three different packing. We use a slightly ellipsoidal particles, and then we generate isotropical packing and also bedding plan in the horizontal direction, bedding plan in the 30 degrees direction here. We look at their difference in the response here. Okay. These are the displacement, dynamic displacement field for the three cases. Left is isotropical packing, middle is a horizontal beddings, and then right is 30 degrees here. So for the left and the middle, and more or less, we see that the dynamic response is symmetric. And then, but for the right, because there's a strong isotropic bedding plan in 30 degrees in these directions, and so this dynamic displacement is no longer this symmetric after the punching here. Okay. We can further make a comparison between this displacement field for the three cases with the excess power pressure generated during this punching one here. Again, there's a strong correlation between the excess power pressure generation with this permanent deformation and in each case here. But we observed that this excess the power pressure dissipation is not fully synchronized with the deformation patterns here. And so the two actually, they are coupled, but they are not synchronized. And also we monitor the displacement of the response of the ground surface A point for the three cases here. They generate such a pattern. You go to this point, for example, this alpha equals 0, 0 case, and then during this loading, punching loading, it will go through this one, going further circles, and then going these circles, and then going to back and to this one. Okay, and so this gives us a very typical Rayleigh surface wave characteristic, and then one where this anisotropy will play a very important role here. Okay, and we can further look at if we use the different permeability for these soils, and their response can make some difference. And this again is served as one kind of this mass sensitivity, is a sensitivity study, and for the response and for this particular problem here. Okay. And the sediment can be different if the permeability is low, and then will give us a low, slow consolidation, and then the sediment comes relatively small compared to a high permeability case here. And then now I want really to show another set of problem, which is sensitive to this temperature. In addition to this hydromechanical coupling, we want to look at the thermal hydromechanical coupling. And so there are quite a wide range of problems in the nature, in the engineering field. That is, we need to consider temperature changes. And due to this climate change, for example, the phase thaw behavior in a permafrost can be issues here. And this is a picture of the thaw caps observed due to climate change or due to a warm season here. And then this thawing can generate landslides, and this thawing again, that thawing of ice can turn into water, and then can further increase this saturation, and then cause it generate the debris flow case like this one here. Okay, and this freezing and thaw cycles, and this especially thawing process can generate a very large settlement in this cold area and cause the infrastructure like a pavement generate such a this real is not exaggerated. The thawing sediment cause the pavement like this one here. It also can generate a crack here. Okay. These are the permafrost, and this can be a very large scale in the cold area, and they important to many countries. And also another problem that with temperature would be the energy geotechniques. One aspect is how we can really to extract this missing hydrate from the deep seabed, also from the onshore, the deep ground here. Okay, in the deep seabed situation, that are the missing hydrate can always is present in the bearing sediment, the soils here. Okay, and once we want to extract it, or in the natural settings, that when the temperature or pore pressure change, and then the missing hydrate can really turn into this the stabilized as-look solid state to a gas state. Okay, both temperature and pressure matters. And once that change really can cause a release of the gas missing hydrate, and then it cause instability of this sediment, and can cause larger scale submarine landslide here. It can also cause challenge for this for our human being extractions. Indeed, because these issues, and then there's no successful missing hydrate extraction so far in the world here. So it's important that I wanted to understand the behaviors and to simulate such a behavior in a more rigorous way. That's why we want to develop a multi-skill and multi-physics approach to tackle that one. There are numerical challenges. We need to consider the thermal, hydro, and mechanical behavior of this missing hydrate. Okay, and then we need to consider this. Also we need to further consider the chemical coupling. For example, because the missing hydrate, when returned from the as solid look and to this gas phase, is decomposition of these chemical components. And then this is the THMC coupling is challenging here. And the whole process involves phase transition from a solid phase to a gas look here. Okay, for the permafrost, it's basically maybe a two-way phase change from ash to water, and also from water to ash here. Okay, and also in the different engineering settings, we need to consider either quasi-static or dynamic loading behaviors. Also, we need to consider light deformation to failure. And so this even we don't consider chemical coupling. And then we consider thermal hydromechanical coupling, and it involves as I showed here, a much complicated physical process and physical property and attributes, right? So this is a recent work by my fourth year PhD student, Ji Du Yu. He just defended his PhD, and then now is actually Dr. Yu, and then the work done. Again, that we use MPM and the continuum level solvers, and then we use DEM again for the particle levels, and we couple the two together. But here, for either a permafrost or a missing hydrogen bearing sediment, we consider a frozen soil, and it consists of soil particles and the S or the missing hydrogen crystal bonded to the part at the contact or fill the pores here. And also there'll be unfrozen soil and unfrozen water in the pore here, right? And so we consider such a frozen soil as a three-phase triphasic assumption from here. And we can develop volume fraction for each phase, degree of saturation for both the S and for the water here. And also we define different density. Okay. And for the multi-skill strategy, and here we consider material point as a mixture of solid particle with cemented S or missing hydrogen. Okay. And then for this for this one, and then plus a unfrozen water. And for the solid particle and cemented S, and we use DM to simulate it. Okay. And here we consider other load like heat transfer, and the different conduction, convection, or latent heat of fusions. But we don't consider radiation, and so this is multi-skill framework. Okay, and then Gaussian equation for the macro material point, we consider the conservation where effect of this volume change due to this S water phase changes and need to be taken into account in this mass conservation, because we know that for a water S, and the S their density is smaller than the water phase, and then the volume for the same amount of mass, and then their volume will be different. We need to accommodate that part in the Gaussian equation here. Okay, we consider this theory of mixture, and then for momentum balance equations, we need to consider their effective stress and in these considerations, and also consider liquid water pressure, and we consider effective stress theory in this case. So for the unfrozen water, we consider Darcy's law in that part. And we consider the light deformation, and we define a Yeoman stress rate to consider the light deformation part here. But we also consider energy balance. Indeed, we incorporate actual terms, consider latent heat effect during this S water phase transition here. Okay, and we also consider Free's law, and then for this heat part of this S and water transition. There are also other assumptions. For example, we consider the equation of state for the solid phase, for the liquid phase of the S phase here. And during the S and the water phase transition, we consider a soil freezing characteristic curve, and then we make an analogy for the unsaturated soil mechanics, and for a partially saturated soil, and then make that analogy and write an equation for the partially frozen soil here. And so this is the equation we have to do, and we also consider the relative hydraulic conductivity for that case here. And again, here we introduce this S phase, and then we use this VPT formulation. Here we consider solid velocity, liquid velocity, because the solid include both the solid particle and the S phase here. We consider the pore pressure of the liquid, and we consider temperature here. We first solve the temperature field, and then we solve the equation. We got an intermediate velocity for the solid and liquid, and then we further solve this pore pressure field, and then from this one, and then we further solve the whole equation for the velocity, and then this will return this the whole set of variables. And the particle grain scale labels, and we do some simplification. And so we consider the S phase will serve as the bond between the particles. This bond will be added to the particle strength, and this bond can be broken and when the quaternion is formed. This bond can be subject to melting as well when the temperature changes here. Okay, and so we consider the S as a S saturation dependent cohesion model and is added to the particle bonding model here. So we apply this principle of effective stress for this solid DEM simulations here. And the physical process we consider the RBE, including this effect of S cementation at the contact levels. And the S content will also affect the bond strength and so stiffness as well. The S bond formation and melting and form these phase changes during this frozen soil here. Bond can be broken and then make the soil strength decreased. Okay, and also soil strength will depend on the strength and stiffness will depend on the S content, confining pressure, and packing density. And also we respect the past and the history dependent the stress-strain relationship during these freeze and thaw cycles here, right? Particle itself can expand and contract rearrangement as we showed before. This is further again that we do some benchmark again here because we involve a thermal effect here. We do is 1D non-isothermal consolidation. And in a normal 1D consolidation, in addition to that, we apply a thermal load at the top here. Here are some comparison with the analytical solutions for temperature, for the settlement, and also for excess pore pressure changes here. Okay, these are the further we compare the three cases and the further comparison here. This is another 2D thermal hydromechanical coupling response that we have a frozen soil domain that we insert a line thermal load here, like a thermal pile. And then this thermal pile was subject to these cyclic thermal cycles here. And then we look at the soil response here. Okay, at the ground surface, there's a fill and drain here. Okay, and we inserted the different RV levels here. So these are the monitoring point at the surface, and we have S0 as Y1, and the deeper part we have M0 to M6 here. So these are the different M0 and M6, and it's far away, and then the cycle it feels less significant close to this thermal source here, and so it's subject to the pore pressure will change cyclically here. Okay, and also the vertical displacement at the 2 points here will also cyclically change with that. And this is the comparison of the excess pore pressure of this coupling scheme or coupling scheme with a pure MPM simulation where we use a considered model. We assume the considered model for this one here. And then we calibrate the considered model parameter by the DM simulation here. So this is the comparison of the two. Comparison is pretty consistent. This is a simulation process. And then when we load it in the freeze-thaw process cycles, one cycle after one cycle, and this white line indicates a 0 temperature contour. And while this the blue one, after that, this one will be like a minus one thing here. Okay, so this is the temperature field, and this is the S saturation field, and this is a pore pressure change field, and this is displacement. And you can see during the typical freeze-thaw cycles, 5 cycles will generate permanent deformation, because when you have a thawing process and then they generate a pore pressure change and also volumetric change, and then that generate a permanent deformation, as we see from here. This is like a typical different material point, M0 to M3, and then the temperature change, cyclic temperature change filled by the 3 points can be quite different. And also here, as I mentioned, that the zero pressure, temperature contour line, and compared to during the different time instance can evolve during this circular loading case. And also, if we use the different models for the S-bound, weak and strong here, and it will have quite different response. For weak one, the vertical displacement we feel at the ground surface can be much significant than strong bound here. This serves as a sensitivity study, and you can actually use that as a calibration process for real engineering problems here. Okay, and these are the cyclic load, and it started at the vertical displacement start from this one and doing these circles, doing these circles, and then going up and generate permanent trajectory and deformation here. This is a medium bound case. This is a strong bound case here. You can observe the magnitude difference as we see from here. And this is further comparison of this pore pressure evolution here. And a strong bound and weak bound, the evolution different here. Okay, and so this is the comparison of this pore pressure for weak, medium, strong here. In the strong case, we observe quite significant excess pore pressure or negative pore pressure change. Why? Because you generate strong bond, and this bond, when the circular load generate pore water, and then you generate excess things that are pore changes, and then the water cannot fill it, and we don't consider air phase, so that you can generate negative excess pore pressure in that case. That will further affect the strength of the soil and will affect the deformation. So that account, we can further correlate with this one with the experimental observations, and this is quite consistent account for this phase saw process. How would that generate the deformation and strength changes? And because this is cyclical thermal cycles. And we further analyze the mechanism. Indeed, excess pore pressure in this the solving process during this freezing process, that during the freezing process, that the total volume is generated by the add up of this S volume, pore water mass, and also pore volume here. Okay, and so there'll be available pore volume, we call VA here, the total is pore volume minus the MS volume. But then the required water volume is basically water mass over this water density. And we compare this VA and this VR, and we find that there's a mismatch during this one single cycle here. And sometimes it's on top, which means that the available pore is bigger than the required one, and then you, in that sense, that you can generate negative pore pressure. But when that is required one is greater than the available one, and that generate positive excess pore pressure. This basically give you a explanation on why the positive and negative pore pressure can be generated during the typical freeze and thaw process in frozen soils here. Here, this is basically the volume distance that we can count, and that give us a thing. Again, this multi-skill approach offers us capability really to look further into details at the different RVE, like this M0, M1, S0, S1. M0 and M1 basically is one close to the thermal source, and then the other is a little bit distance, and then their deformation can be different. is for the surface of soils and their shear deformation generated by this soil heave and can be quite significant. I wish further to offer two examples to demonstrate that. And then this case is for the missing habit bearing sediment case here. We consider a submarine missing habit bearing layers like this one, and then this layer is existing for optimal condition where the temperature typically is 2.3 degrees, and with a surcharge is 3.75 megapascal here, and then and the gravity is stable, and then at the bottom of this sediment layers, and we increase the temperature to 10 degrees here, okay, and then the total length of this one up to 25 meters to this time, okay, and we look at this problem. This is how we when the sediment is heating at the bottom, and then this missing hydrogen will be dissolved, and then the gas, we release the gas and let that part to remove from the simulation, and then when the dissociation of the missing hydrogen in the sediment occurs, and then the strength is lost. They generate this collapse of this missing hydrogen. And the top basically give us the topical strain, and the second is the displacement, and this x and y, and then this fourth one will be excess pulp pressure here, change during the process. The bottom is a hydrate saturation that we can show from the process here. Okay, so this is one example that we show that we can use this thermal hydromer kind of coupling framework multi-scale approach to simulate this submarine landslide triggered by this hydrate dissociation here. Okay, this is the further recap of this topical strain at a different time instance, and this is indeed a so-called retrogressive progressive video of this one, because the collapse at the top part, and then it caused a further collapse and from the left part here, and cause and make this run out thing here. Another examples, and again that I want to use this footing problems here. And here the footing problem is different than previous one, is pure hydromechanical. Here we consider the thermal effect here. Now we consider a frozen soil foundation, and the initial temperature is -5 here. And then it's subject to dynamic footing. Here, footing is not quasi-static, can be dynamic here. And then the footing have a surcharge of 20 kilopascal. And also we have a thermal source. At the free surface, we apply a temperature of 20 degrees. And so indeed, we're going to heat the ground. And then, so the soil will be subject to both the dynamic footing at this part, and then have a thermal heating at the ground surface here. Okay, and then so the force is ramp up from 0 and to this level here within this time here. So this is the prediction, and so on the left we have a control group where we don't consider the melting process. On the right we consider a melting process and this dynamic and heating thing. Here we monitor this -1 degree contour and 0 contour, and on top here. And so this is the comparison of the two here. So apparently, if we consider the mass as melting, and then the thawing case will have quite a significant difference than this unmelting case here, unthawing case here. And also, if we compare the so-called resistance or loading bearing capacity of this footing, and then if we don't consider the thawing, this indicates a blue part, the resistance is much higher than if we consider thawing or salt. okay, totally the final case. And then the difference can up to more than 30 or 40%. Okay, and which means that if you don't consider thawing effect in the frozen soil condition case, you would overestimate the bearing capacity of this foundation by 30 to 40%, and which is unsafe here. This is the simulation results. Again, we compare this. The two left is the unthawed case. That case is a thawing process. The two contoured indicator -1 degrees contour line and 0 degrees contour line. Okay, and this is the temperature field, and this is the diatomic stream field, and this is the pore pressure field, and this is the displacement field here. Okay, and so there in this case that the effect of this thawing is quite apparent. Okay, and also remember that this footing is a dynamic footing. We can apply different loading rate and from a very slow loading rate to a high rate load to from a 0.25 meters per second to 2 meters per second. And their process can be different. It really reflect a competing mechanism of who is dominant. Is the mechanical load of footing or is a thermal melting process? Okay, when the penetrating rate is slow, and you can see here the solving process, solving front is much faster, deeper than this mechanical shear band here, right? But when the footing penetration load is faster, you can see the shear band can really to lead in front of this solving curves, and also make the solving curves very kinked in somewhere here. Okay, so this is a competing mechanism that we can also capture and during this footing process here. So here is some quick conclusion before I finish here. And so this MPM+DEM coupling is basically a extension of this FEM-DM multi-skill coupling to large deformation problems. And further, we can really incorporate this multi-physics problem, thermal hydromechanical coupling processes to tackle more challenging problems here. We use several different classic geomechanics problems involve phase transitions, like phase thawing frozen soil, and also hydrate dissociation in the missing hydrate bearing sediment to showcase advantages here. Okay, we can further the ongoing work is further incorporate this partially saturated granular or more complex problems here.
Why the formation is sort of triangular in nature? Do you have anything to say?
The triangular shape basically is a shear band. Because it is subject to a gravity, and then also the the seabed, right? The confinement is high, so you can consider that this sediment is subject to some hydrostatic pressure at a very deep seabed. Yeah, and then this is basically a shear band occurs at the beginning. This part is heated, and then there are certain inhomogeneous deformation formed. And so this is a triangular shape shear deformation occurred. And so this part, because they lack the lateral support, and then this will break away and form this first step of the shear band here. And then this move away, and then this part will lose the lateral support, and so this will form a second this part of the shear band again here, and this will further will be propagated leftwards, and then will the right hand side will move away from the body. So this is shear
Yeah,
band feeder patterns.
yeah. So the height of the domain that you have taken is sort of 5 meter, assuming that the bottom portion is firm. But if you increase the depth, you have anything to comment on how the failure will look like? Will the propagation will happen till the firm layer or till the boundary? the bottom boundary, or will it change? Because
No,
in
the bottom
classical,
boundary here we consider as a relatively smooth boundary, and then of course you can give a certain friction, it doesn't matter, and then but the failure pattern pretty much is quite consistent. This is not only happening in the submarine landslides, this missing hazard case. If you really look at some kind of like we call a quick clay in the Nordic area, the quick clay can also happen in the failure like this. We call it retrospective progressive failure. And
yeah,
so it's typically happening in the loss of strength, lateral support of strength, and then of course the strength can matters. And if your strength happens lost not in such a way, it can really to do a spreading failure case here. But
yeah.
this
Thank you.
triangle is quite a common failure patterns.